going to be presenting our paper on I/O speculation for the microsecond era, and this is work we've been doing at the Non-Volatile Systems Laboratory in collaboration with our co-authors at the IT University of Copenhagen. And the main idea of this work is basically that in the near future, I/O costs will shift to the tens of microseconds, which is different than the kind of I/O latency that we're used to today. Current strategies for dispatching microsecond I/O is suboptimal, and we think that speculation can help. So we're going to explore several speculation techniques, and we're going to identify research challenges that we think need to be overcome for speculation to be an effective technique. So we live in the millisecond era right now, and that means that I/O is generally pretty slow, but things are changing across the board. Networks, PCI Express, and storage are all getting faster for several reasons. For example, we're eliminating software overheads, and the hardware is getting a lot better. So we're actually at the dawn of the microsecond era. And in the next slides, I'll focus on storage, which has actually shown the most dramatic changes with respect to I/O latency. So let's take a look at the evolution of storage from the hard disk. To the left, I think, is the IBM 350 RAMAC, the first hard disk. It's got a latency of about 800 milliseconds, and in about 50 years, the hard disk, has improved just barely compared to the increase in capacity. So today, you can buy a SATA hard disk, and it'll only have tens of milliseconds of latency. So the hard disk era is the millisecond era, and things are changing, though. Today, you can buy a NAND flash-based solid-state disk, and it'll have access times in the hundreds of microseconds. Or you could buy, or in the future, hopefully, you'll be able to purchase a phase-change memory SSD, and it'll have access times in the tens of microseconds. And you notice that these access times are all in the microsecond range, which is how the term microsecond era comes. And what this means is that most of the I/O that in the next decade will probably be in the microsecond range. And with any shift in technology trends, such as latency, we have to re-examine how we build our system. So in this paper, we examined the current techniques that the operating system employs to dispatch I/O. And those two primary techniques are known as yielding and polling. Let's take a quick look at what yielding is. So under the yielding strategy, when an application asks the operating system to dispatch an I/O request, the operating system puts the application in I/O wait state and dispatches the request to the actual I/O device. While the device is writing, another application gets to be scheduled in and gets to do some useful work while we're waiting for the I/O request. Eventually, the device sends an interrupt, and that allows the operating system to stop the second application and eventually schedule back the original application that requested the I/O. So this is great because it lets another application run while we're waiting for the I/O to go on, but it's got a cost. We have to pay a lot of context switches between the first application and the second application and the operating system, and furthermore, we have to pay for scheduling costs because the first application might not necessarily be scheduled back right away. We're kind of at the mercy of the scheduler and whatever other tasks are running on the system. And of course, there's other secondary costs like cache pollution. So yielding is a great technique, except that it might cost us hundreds of microseconds for each I/O request. And if we're in the microsecond era and I/O is only going to take a few hundred microseconds, then this technique might be too expensive. So, and in the next talk, I think they're going to talk about the yielding strategy. There is another strategy called polling that's employed, and it's usually employed for very fast devices. And a brief look at how this mechanism works is basically, in the polling strategy, when the application does an I/O request, the operating system actually just keeps on asking the I/O device if it's finished. And once it's done, it goes back to the application. So this this technique is a lot more efficient because we don't have to pay the cost of scheduling and the number of context switches is pretty minimal. But we had to pay the cost of polling, which is basically a period of time where no useful work can be done. And so if the time the application if the time the I/O device takes to do an I/O request is actually significantly long, then we can be wasting our time just spinning and doing no work at all. Let's take a look and contrast yielding to polling. If you look at the top, we have polling. So polling is great when the device is going to take a long time because it will allow us to have concurrency. But once the I/O cost is below a certain point, we start having to pay the overhead of cache pollution and scheduling overheads, which is going to be greater than the actual time the device will take to do the I/O. And when we do, sorry, yielding and polling are flipped. Didn't realize that. Okay. But when we do polling, which is on the bottom, polling is very efficient when our I/O time is very short because we really can't do anything better without paying some kind of cost. But when we do yielding, as we reach the microsecond range, polling starts becoming pretty expensive because we basically are holding the processor to do nothing. So the question we had was, is there a better technique that can satisfy this middle range of microsecond I/O requests? And that's where we get to speculation. So very basically, in the speculation strategy, what we do is we create a checkpoint, and we allow the application to speculatively execute. So we pretend that the request is actually completed successfully, and we let the application continue running. We monitor the application to make sure that it doesn't perform a side effect. For example, if it goes and tries to kill another application or communicate the results to another application, we have to stop and wait for that I/O request to actually finish because we need to know what the result is. And this is the waiting period. And then once that device write finishes, the application can continue running. We'll commit, and everything continues as normal. Now, if the write fails for some reason, we've created this checkpoint, so we can basically use that to erase any speculative execution that occurred. So this is great because we have the minimal number of context switches just in and out of the operating system, but we had to pay the cost of creating this checkpoint and the cost of waiting. So speculation is a great technique because it allows the application to continue to run during the I/O while it's doing I/O. It's actually been employed a number of times in the literature, and we'll talk about that. But there has to be enough instructions to speculate through. So we took a quick look at that. Basically, we wanted to make sure that speculation is still a useful technique in this microsecond era. So we took a look at the time and frequency between various system calls and side effects. So what we found was that while there are some applications that don't do any work between I/O requests, like, for example, DD, which just copies blocks over from one device to the other without doing much work. But we found that database applications were great because there were plenty of instructions or work that it did between a system call and another system call. So we took that as that there was potential for us to speculate through. So we examined 5 different speculation techniques, and some of these techniques have been proposed in the past, and we wanted to re-examine them in the context of microsecond scale devices to see how they would work. So we took a look at software-based checkpoint speculation, which basically involves creating this checkpoint using software. And it's been used by a number of systems in the past, and basically what these systems generally do is they use the clone system call to create a checkpoint, basically copying the virtual address space of the application and using that to roll back if the write fails. Well, what we found was that the clone system call is actually quite expensive. Even for small applications, the cost of clone could be anywhere between 30 to 50 microseconds. And as the application sizes grew to be reasonable sizes, we quickly started getting to the millisecond range. So it seemed that software-based checkpointing might be a little too slow for our microsecond devices. So we then looked at hardware-based checkpointing. So the idea here is to basically leverage Intel's new transactional memory extensions. And we found that those extensions had a very low cost to create a checkpoint, which is great, which is what we wanted. And you could write a significant amount before you basically ran out of space to create the transaction. But we found that while this technique works in something like a RAM disk, in real I/O devices, I/O operations cause TSX to abort, which is not actually the behavior we want because it basically destroys the checkpoint and we have to start all over again. So while hardware-based checkpointing could work, we need to maybe work on changing the interface for transactional memory so that we don't always abort. The next thing we looked at was checkpoint-free speculation. So the idea here is that while checkpoints cost a lot of checkpoints have a high cost, so maybe if we eliminated a checkpoint, we could get better performance. So we found that checkpoints are rarely used. The results of a write are always successful. So what if we assume that every I/O succeeded? In order to do this, we'd have to change programmer expectations. But in our system, we had some issues with memory copies, and that didn't perform as well. We also looked at prefetching, which is targeted towards reads. We found that microsecond I/O devices have a lot more IOPS to spare, and that prefetching correctly is more profitable in microsecond devices than nanosecond devices. So it might be worth revisiting aggressive prefetching systems because we have all the spare I/O. And we also looked at parallelism, which was used by systems in the past, and that would be useful because these new devices offer a lot more parallelism. So in conclusion, microsecond I/O is coming. The current strategies aren't optimal. We evaluated several techniques, and we see several research challenges that we identified previously that we need to address as a community in order for speculation to be effective.
I have one question.
Sure.
Philippe from North Carolina State. The paper reminds me of the 2012 paper, Is Polling Better Than Interrupt? I was wondering if you compare the performance of polling, interrupt, and speculation in any kind of form.
Okay, so the question is if we compared polling to interrupt and speculation. No, we didn't, I guess is the best answer. So polling is going to always be, so we couldn't actually get speculation to work effectively for microsecond devices because of the performance overhead. So in our, polling would actually be more expensive anyway because as he's about to tell you, polling is too expensive if you're going to be waiting for hundreds of microseconds.
I have a quick question, actually. I like a paper I read about it. There's one thing that sort of confused me, if you can clarify that for me. Is it a case that speculation is to help writes and prefetching is to help reads, or they help both? That's sort of my impression, but am I wrong or am I right on that?
Yeah, I think you're right, because speculating on reads is a lot harder because you actually have to come up with a result. And there's ways to do that, but prefetching is also technically speculation because you're performing reads before you know that the reads will actually be useful. So that's this distinction there. And
oh yeah, so you're basically saying prefetching is speculation.
Kind of speculation,
okay, got it.
Yeah.
All right, thank you.
Yeah. But you could also speculate on the value itself, and that would be a lot more difficult.
All right.
Yeah.
Thank you.